And okay, so it's 6 when we were expecting to finish. I think we've not done badly considering we started quite late with the session. And I'm delighted that our final speaker, Michael Hecht, has been able to join us from MIT. Michael is going to talk to us about, let's get the title right, the Now Making Oxygen on Mars, MOXIE and the Perseverance mission. So, Michael, over to you.
Thanks so much, James, and apologies for being late. I'm keeping track of time zones in Boston, in California, where the mission's headquartered, and in Jezero, what I'd like to call Jezero Standard Time. Most people just call it Mars time, and I can't seem to figure out European time. I apologize profusely for that. And it is an exciting time, as I mentioned. Perseverance is on Mars, and some of this is basic. I really don't know how much everyone in the audience has been thinking about Mars, since for ISRU these days, a lot of focus is on the moon. So Perseverance, I'm sure you know, landed on Mars on February 18th, and there has never been a mission instrumented for selfies the way that Perseverance is. And I'm sure you've all seen, if you haven't, go look on the NASA site, the videos of the rover being lowered from the sky crane down onto the surface. There's also some astonishing animations of the entry, descent, landing sequence. Of course, no selfies there, but you can see the final stage in this clip from the video showing the dust blowing around the surface. And it was quite an astonishing event. It's hard to believe this landing system works at all. And of course, we captured the landing from HiRISE, the HiRISE imager, and you can see the parachute on the right as the sky crane is carried down across Jezero's crater to the landing site, where it finally came to rest right there. Right near a boundary of some area we really don't want to go. And this was not by coincidence, because it was instrumented with terrain relative navigation for the first time, which isn't quite pinpoint landing, which of course we'd like to do someday. We'd like to say land in that spot. But what we can do is land in rather cluttered terrain like this and find a good spot with the terrain relative navigation. And that is an investment forward into future larger missions and human exploration missions. In fact, you can see again from HiRISE the landing of the lander on the surface is quite well defined. At least you can tell it is longer than it is wide, and you can also see where the light areas where the surface dusty material has been blown away over quite a large area, which tells you that in any mission that wants to look at a pristine surface needs to drive, and that's partly why, of course, we have wheels. We immediately saw, this rover is instrumented with cameras everywhere. We immediately saw some stunning terrains out of just the navigation cameras alone for the rover. And how these navigation cameras have progressed over time is also quite stunning. And this would keep geologists happy for a lifetime. But we didn't have to settle for that, because we have, in fact, a much, much higher precision zoom lens capability on the so-called Mastcam Z, or Zcam for short. And just to give you an idea about the difference of these two, other than the colors, et cetera, this is the kind of resolution you can pull out of Mastcam Z of that little tiny distant object. And this is a rock. I could give a whole talk on naming schemes and how they've evolved. You can't talk about anything if you don't name it, but this quickly picked up the name harbor seal just because it looks like a harbor seal. And you can see the scale on that 50 centimeters. So quite astonishing ability to image. And I could go on to go with the other instruments, but I'm here to talk about MOXIE. And MOXIE is inside the rover. You can see the designation here. I just mentioned that in many ways, the centerpiece of the mission is this coring drill. And a lot of the reason for almost everything else is to figure out what cores of rocks and regolith samples to put in a cache to be returned from Mars in a multinational mission, still being defined sometime in the next decade, when we'll have our first curated samples returned from Mars. And that will also be, like MOXIE, that will also be an important step in the path toward human exploration. I mentioned cameras anywhere. I'll skip over that in the interest of time. I was up early this morning, local time, not so much your time, watching the first flight of the Ingenuity helicopter. And, I've always been intrigued by the name in situ resource utilization, and always pointed out that we've been using resources for a long time. Every time we use a parachute, we're using, the atmosphere as a local resource. And so I look at this and say, well, you're using the air on Mars to provide lift for a helicopter, for a drone. Isn't that a ISRU? And the important, that's kind of a rhetorical comment. The important point is what we mean by ISRU is generally not this. It's generally transformation of resources. When we find resources and use them for something else, not just in a, if you will, in a passive way to provide lift for an aerial vehicle, which of course is tremendously important in its own right. But that flew this morning, and there should be a press conference coming up in an hour or so on NASA, where we expect to see high-resolution videos of at least part of that flight. But anyway, that's a long introduction to get us around to MOXIE, which is a significant in many respects, and in part simply because of the enormous investment that NASA has made after many, many years of thinking about what we need to do to get humans to Mars. They've made a very substantial investment in actually trying out a key piece of technology on Mars that will be part of that strategy that's going to get people onto the red planet. And I'll tell you about that strategy in a moment. But what MOXIE accomplishes is it demonstrates that a key resource, oxygen, can in fact be extracted, or it will demonstrate that it can in fact be extracted from the Martian air, which is almost exclusively CO2 and has only a negligible amount of oxygen. Now, of course, you could go find ice on Mars. We know where it is. It's quite a bit to the north of where we landed, but we could go find it and get oxygen that way. The beauty of getting oxygen from the air, well, that's what trees do. You don't have to go anywhere. You can be a tree. You can stay in one place and get oxygen out of CO2. It's a scale model, not even so much because we couldn't do more in terms of mass and volume on the rover, although that is limiting, but we're extremely limited by power on this rover. And, a full-scale system of the sort we'll need to fill up an oxygen tank, for a human mission would require tens of kilowatts of power, and we've got about 110 watts. So what will MOXIE do? Well, it's going to make between 6 and 10 grams of what's called here propellant grade, that's also breathing grade of oxygen per hour from CO2, which is most of the thin air in Mars. The air is less than 1% of the density of what the air is here on Earth. And just to get, sort of oriented, that's about half of what you're breathing as you're listening to this talk. And it's kind of what a modest-sized tree will produce. Took a tremendous, enormous number of people in different areas and disciplines and places to pull all this together. And we're on Mars. So very quickly, the standard model, if you will, there are other models and some being looked at actively, but the standard model for getting people to Mars uses the simple Holman transfer. I like to draw the analogy to changing lanes on the highway, where you just push off a little bit from your lane and drift into Mars lane, but you have to do so that Mars will be there when you get there. And that limits it to one cycle being 26 months. Every 26 months, Mars is bright and shiny in the sky and rises at sunset because the Earth overtakes Mars in its orbit in what's called opposition. And that opportunity comes once in 26 months. So you take that opportunity to go to Mars, you wait till Mars comes all the way around the sun back to here and head back to Earth. And as you can see, that's a stay of a year and a half or so on Mars and a full mission time of close to 3 years. It's a long way to go. And the general model, again, the model is kind of canonical, not necessarily current. has been that you start with a cargo mission. You send everything you need in the cargo mission: a habitat, a power supply, rovers, a power plant, and critically, of course, an ascent vehicle, so that you can get back home. The scenario in the movie The Martian recently. We don't want any more Mark Watney stranded on Mars in real life. So you send all that first, and then you send the human mission with the transfer vehicle, what they need to keep alive to go to Mars and to get back, and incidental supplies for once you move into the habitat that's already been constructed on the surface. That's the canonical model. And this is more of obviously a cartoon I put in for different audiences, and I think everyone here is probably aware of this, but just briefly, anything that uses fuel, including us,
5 minutes.
That's fine. Needs to breathe, and in this case, what we don't recognize on Earth is that the oxygen weighs several times the weight of the fuel we use, whether that's gasoline, whether that's a log in a fire, or whether that's rocket fuel. And so while you could fuel that ascent vehicle to take 4 astronauts home from Mars with 7 tons of methane, you'd need about 25 tons of oxygen. Okay, and that's the single biggest thing you need to take with you to Mars. So if we can eliminate that, that's the strongest case for ISRU you could find on Mars, and the raw material, the CO2, is readily available. So what we do is we use an electrolysis cell. This is a high temperature cell. It runs about 800 degrees C. There are lower temperature technologies. It turns out, the high temperature isn't really that much of an obstacle. And it doesn't, if you insulate it well, it doesn't waste much power. It's otherwise a very efficient system. And what we're doing is we're doing a sort of a classic electrolysis, CO2 going to CO and O, and it's essentially a fuel cell where you run it, in the opposite polarity. So if it were a fuel cell, you would feed in CO, or hydrogen, but in this case CO, and plus O, and get CO2 out. And we do that rather than go all the way to carbon, because carbon is pretty nasty stuff. It would deposit on this device, and it would destroy the device. So we have to carefully pull off just one oxygen atom from the CO2 to make CO and oxygen across that, and bring it across this membrane that selectively pulls out the oxygen, completing the as an ion, completing the circuit by sending 2 electrons back through a wire. So if you simply measure the current that you are putting into the system, you know exactly how much oxygen has gone in the other direction. The way this is assembled is as shown here. You have to have a compressor, and this says a pump here, to pull in the CO2. You have to preheat it, run it through this so-called SOx, and that does the separation from oxygen to CO2. And you can see here the materials: a zirconia-based electrolyte, a nickel-ceria-based cathode, and a perovskite anode that combine and interconnects, a steel, a CFY, sintered interconnects that flow the gases, the CO and the CO2, through the cathode side and pull the oxygen out of the anode side. And the amount of oxygen you can produce is a function of the area, the square centimeters on the surface. So what you do is you stack a bunch of these up in series. And we've done that here with 10 of them from MOXIE. A future system would have quite a bit more. So we put together the scroll pump, the mechanical pump, and the system. We have to insulate it thoroughly. Once it's insulated, we have to secure it by springs, because insulation is not a great mechanical protection against launch and landing, and assemble the whole thing. On the right is the actual SOXY and its assembly, and the left is the compressor. The case goes around it. The whole thing gets put in gold-plated surfaces for thermal control, and the whole thing gets put in a test chamber, and there it is in the test chamber, ready to be tested. Here it is being lowered into the rover, Here it is looking from the bottom of the rover where you can barely see it anymore. Then the rover gets flips upside down, and we realize we never run it upside down, but so far so good. And when you're all done, all you see are some tubes with Mars oxygen coming in, Mars atmosphere coming in, oxygen coming out, and an inlet with a HEPA filter, which is its own interesting talk. So from the outside, this is all you get, is just that filter pulling in the air. What's next? And I think I will probably close with that. We landed on the 18th of February. We did an aliveness test on the 22nd, always good. We ran with what we call a run control table on Sol 13, and that's where we go through the steps of, run the temperature to this setting, run the compressor to this setting, run the voltage to this setting, turn on the control systems. We did that on Sol 13. On Sol 14, we did a health check to actually run those heaters and compressors, not just turn on the table. On Sol 55, we did a compressor sweep to calibrate the actual flow, since the atmospheric density is so variable that just knowing the speed of the compressor doesn't tell you how much gas you're getting. And we are supposed to get, tentatively, first oxygen on Sol 59, or the morning of Sol 60. So, and what does that mean? Well, it is now about 2030. I'll tell you exactly, it is 2103 on Sol 58. I was supposed to give the talk a little earlier. And we're currently penciled in, I won't say more than that, for oxygen in about another day. So we would get it Tuesday if all goes well. And let's see. So anyway, I don't think I'll talk, just a point about full scale. As I said, we need 25 to 30 kilowatts of power. We need to produce 2 to 3 kilograms per hour of oxygen. We need to do that for about 12 months to get ready for the crew to arrive, and that would assume a crew of 4. And that, fortunately, is about the size power plant you're going to need to maintain a crew habitat anyway. So we're not talking about a huge separate power system for this. It's the same power system. And we're making progress. So I really want to conclude with this. Oxeon Energy, which was the child of the company, Cerematech, that originally made this Oxy stack, has already developed prototypes of a stack that can produce up to about 1 kilogram an hour, as compared to the 10 grams we're making now. The company Air Squared that developed the compressor is already developing a scaled up version. We're looking at carefully at MIT about how to make the filters smaller and lighter. And we think a very conservative envelope for the final system is about 25 kilowatts power, weighing a ton in about a cubic meter. And other than that, just thanking everyone, including 3 different directorates at NASA: the human exploration, the space technology development, and of course the science directorate that brought us the whole mission, and lots of people, lots of companies I've mentioned, etc. If you want to know more, there is a very nice review for actually a review issue of Space Science Reviews that just came out, and this would be the MOXIE paper that will have all the nitty-gritty details. I'll leave that up if anyone wants to jot down the reference. And I thank you for your attention. I'm sorry if I ran a little over. Happy to take questions.
That's great. Thank you very much, Michael. And what a way to go out the session. I mean, I find it personally absolutely extraordinary that we have an ISRU plant running on Mars now. I mean, that's we, in the opening talk, the president of ARSI was telling us about how he used to think of, as a kid, reading sci-fi books and thinking about the future. And I think that's just an extraordinary and inspirational part of what is an extraordinary mission.
Yes, and I'm very grateful to Andy Weir for putting out The Martian in such a timely, way, so that everybody knows what it is, just what it is that we're doing.
That's wonderful. So one question, you talked about the scaling up and things. I wondered if are there any particular environmental risk factors or other unknowns about operating this on Mars that are really distinct that you need to do on Mars that you weren't able to simulate or to understand sufficiently in a terrestrial laboratory?
Yeah, that's a very difficult question. And to some extent, it's as Jeff Hoffman, who's the deputy PI, likes to say, and he's flown in space 5 times. He knows this. He said he likes to say test beds are doomed to succeed because, of course, you build the test bed to test for the things that are problems, and those won't occur because you've planned for them. But yes, there certainly are things you can't simulate well on Earth, and to some extent just from sheer complexity of putting everything together. From, I don't think low gravity is an issue, but the dust-laden atmospheres with huge temperature swings. Radiation is not that big a deal compared to other missions that we do. But the gravity does affect things like convection and winds, which affects air intake. Filters behave very differently in Mars and Mars environment. We've tested as much as we could. We expect surprises, to be honest, and we learned a lot of surprises as we went along, and find that not everything works in a Mars environment the same as it works on Earth. And one thing I keep pointing out, we've never tested, we could, is we haven't run this instrument for 2 years, right? Simply putting it in a closet and not running it for 2 years and then plugging it in and saying, does it still work? That's the kind of thing that you don't think about, that can go wrong in a real mission.
Well, thank you very much indeed. I think we'll need to draw the session to a close at that point. I think it's just wonderful that what we've seen this afternoon is we're visiting asteroids and taking samples and finding out things with it, some extraordinary missions. We're generating oxygen on the surface of Mars, and we're preparing to extract ice and make oxygen and metals on the surface of the Moon. I think it's an extraordinary time. Tremendous change and some really exciting things happening. And I hope, thank you to everyone for joining. Thank you everyone for sticking with us to the end of the session. And I think there's some fantastic things to come over the rest of this week. So thanks again to all of our speakers. And I'll hand it back to Lisa. Thank you.
Thank you so much, James, and you were cracking the whip there, keeping to time. I know you have to rush off now to feed your children, like a few others, no doubt. But even so, we've had a minimum of about 400 participants online all of the time, going up to about 800 at one point as well. So thank you, everybody here in the room. Thank you for all of you joining us online. Very active chat going on all the time as well, with a lot of thanks for the great speeches that we've heard, the presentations this afternoon. Tomorrow afternoon, we'll continue with utilization scenarios with Melchiorre Conti, and then regulation frameworks, which will be chaired by Matthias Link and his team as well. Just to remind you, you can continue networking in the lobby online through the course of the night tomorrow morning, Luxembourg time, if you want to. And don't forget to check out the posters as well. So we bid you farewell from Luxembourg for now, live, but we'll see you back here tomorrow afternoon. Thank you. Thank you.